Yeah, so good evening and good morning. Just one quick announcement. Next week, there won't be any lectures. It's traditional to have a fall break. In fact, this is the week of fall break at Princeton, and I'm sure you're all pretty exhausted as I am. So, and give you some time to catch up on materials you want to review with your local instructors. Anyway, any other questions or comments? I should also say last time, there's about 5 minutes of last time's lecture, which is you should just forget, and I'll just correct myself in this morning. Yeah, okay. Any questions? Okay, so today we are going to hopefully conclude our discussion of the Z2 gauge theory. And we obtained this in our discussion as a model of antiferromagnets, spin liquid phases of antiferromagnets, and also non-spin liquid phases. But today we'll see that it's also connected to some other set of experiments on Rydberg atoms, very recent experiments, where the connection is a bit different, but also very instructive. Anyway, so for now, this is our Hamiltonian we're trying to understand. There's a bunch of qubits which act with similar links of the square lattice, labels. And then there's a flux term, which is the product of sigma z around a loop. So this, when k is large, this wants product of sigma z around every loop to be 1. And then there's a non-commuting term, d, which is a field, transverse field in the x direction on every qubit. So this is the Hamiltonian of the Z2 gauge theory in two dimensions. On the square lattice, you can define it on any lattice. And the important property of it is there's an infinite set of conserved charges. The product of sigma x on all the loops connected to the site I. So there's one such GI for every site. And it's easy to check, this commutes with the Hamiltonian. And our connection to antiferromagnets tells us that this gate charge has to be plus or minus 1. It's plus 1 for integer spin and minus 1 for half integer spin. And this was going to play an important role in the first part of our discussion today. So then I talked about the ground states, and we're just doing perturbation theory in small g. So at g equals 0, you want this flux to be plus 1. And one state the flux is plus 1 is all spins up. And to make a gauge invariant, you put this factor, 1 plus GI, eta over there. Okay, and this is explicitly gauge invariant because now you can hit GI on this state and see you get, and use the fact that GI squared is 1 to see that this is an eigenstate of GI with the required eigenvalue. All right, so now if I take this product and expand it out, then I asserted that this was eta to the power of sites enclosed with the sum over closed loops. But very important point is that these closed loops sit on the dual lattice, and this was the source of my confusion last time. So the spins are sitting here on the links of the white lattice. So when I hit GI on a given site, say I hit GI on this site, I'm flipping the spin here, 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 and here. And what I do is I just draw a line through the flipped spin. So for this particular rectangle, I've hit GI on this site and on this site. And the net result is that this spin is not flipped, but all the spins on the orange line have been flipped, and so on. So, and this particular loop includes 2 factors of GI, so it contributes eta squared to this prefactor. This would contribute eta, and in fact, here you have 4 lines meeting that's allowed, and then that the dimer mapping that I mentioned doesn't work because of this. And also because it's in the dual lattice, and I got confused between sigma z and sigma x, which is a very common thing in this field. All right, but So forget that part. This is the statement that we made. Then I put the system on a torus, and I stated that this state, at least at g equals 0, was degenerate at exactly the same energy, which is easy to check. And in this picture, what does this mean? This means that there's a Vx line, which is, let's take it in a straight line. Vx is the product of sigma x on any loop encircling the torus. So instead of just getting closed loops, you get one loop that goes around the torus. Okay. So what this would mean that here's my torus. Then I have one loop, and I'll try to now respect the color. So Vx is always an orange line. So let's imagine Vx is going this way. So this is the ground state with Vx going this way. But now if I take my other Wy, which is on the direct lattice, Wy, remember, was the product of sigma z, then what I've done is put a Z2 flux here through the whole of the torus. Wy is going to be -1, because Wy and Vx anti-commute with each other. And so I have a state with flux -1 through the whole of the torus. Okay, so that's the action of Vx is like the same as inserting a flux through the whole of the torus. Okay. All right, so hopefully that's all perfectly clear. Any questions? All right, so now actually I want to make an exact statement, which I didn't make last time, which is very helpful to understanding things for all g, for small g, and gives us why there's fourfold degeneracy in the ground state. But now let me look at the following thing. I want to introduce another set of operators which also commute to the Hamiltonian. So we have the GI. If I make a list of everything that commutes to the Hamiltonian, there's the Vx and Vy. But there's another set of operators on a torus, and those are the translation operators. These also commute. I can translate the whole lattice on a torus, provided I have suitable boundary conditions, just L by L torus. These also will commute to the Hamiltonian. Okay. So now you can ask about, as when you're doing angular momenta, you have Sx, Sy, and Sz that commute to the Hamiltonian. But then you can ask, what about the commutator between Sx and Sy? It's not guaranteed to be 0. And similarly, let's ask now, in fact, the important commutator would be, for example, the commutator between Tx and Vy. What is that? Oh, sorry, I'm going to take the product. The anti-commutator, that's not trivial here. Excuse me. Okay. All right, so we take Tx and Vy and ask, well, how does that relate to, let's just try to evaluate Tx and Vy on any state. So here's our lattice. And I'm going to let me just take a straight line. This is my Vy. And I'm going to translate it. So this is the state I'm considering. There's some state, and I hit the operator Vy, and then I'm going to translate it in the x direction. Okay, so if I translate it over, it's going to come here. How can I do that operation on any state? Well, you can see that translation is completely equivalent to putting in a bunch of square loops like this. If I put a GI on every such site, then I'm going to basically cancel the sigma x over here and put it over there. All right. But each of the GI is equal to eta. So that's beautiful. It doesn't depend on the state. Every state in a Hilbert space has GI equal to eta. So from this, you can then conclude that this is equal to eta to the power of how many directions you have in this direction, which is Ly times Vy times Tx. So in this case, you translate the state without the Vy and then hit Vy, which is equivalent to what we just did. Okay, so there is this factor here, so not equal to times. So Tx and Vy don't commute with each other. Sometimes they anti-commute, but eta, especially, but for the case where eta is -1. So there's an immediate implication of this, that for eta equals -1, the ground state can't be trivial. By trivial, I just mean, some non-degenerate state which doesn't care about the geometry of the system, doesn't care how big the system is. You just determine some local ground state here, and you just don't have to worry about what happens at infinity. You don't have to care about whether your system size has size odd or even. It should be the same. So if I had a system size odd in both in the x and the y direction, then these operators will anti-commute with each other. And that's something that should be satisfied on every state in the Hilbert space. And now it's impossible for a single state to have operators that not anti-commute on it. So it immediately tells you there must be some degeneracy, depending on when the system is even or odd in any given direction. At the least, I think you can have a 2-4 degeneracy for this algebra, and similarly a 2-4 degeneracy for the other algebra. So there's another, on the square lattice, there's another 4-4 degeneracy emerging here.
Which other algebra?
Oh, there's Ty and Vx. So there's three different things to consider. Well, okay, these are exact statements for any value of g, not at g equal to infinity. You have Tx with y is equal to plus or minus 1, depending on the system is even or odd. You might Tx, and then you would also have Tx. Okay, so this is a very significant statement. It tells us there's something non-trivial going on. It doesn't tell us that there's what we call topological order. That depends on the value of g. So for g small, we in fact have found a topologically degenerate state by hitting this Vx and Vy. And that's fine, and those states can erase themselves to satisfy this algebra principle. You have to take some proper combinations of them and look at the details of the wave function, and they must satisfy this algebra on system which has an odd number of sites in any direction. But what about as g goes to infinity? So as g goes to infinity, this now tells us something non-trivial. That even the large g state, which at least for eta equals plus 1 was trivial, now can't be trivial. There is no trivial state at g equals -1, which is of course a very important case. That's the half integer spinor half case we're most interested in. And what we're learning there is that first, for small g, you could get a spin liquid. That's wonderful. But if you didn't have a spin liquid, there's still something non-trivial has to happen. Yeah.
But even in odd cases, these are two different theories in the continuum?
No, they're the same theory. This is just a global constraint. It's only present on the torus. But that's sufficient to rule out, kind of a ground state that doesn't know about the topology or the size of the system. Yeah.
Is there anything at all like this in the underlying spin system?
Is there one?
You started with the Heisenberg anti-field.
Yes. Yeah.
Does it have anything else?
Oh yes. So in one dimension that's called the Lipschitz-Mattis theorem. Proving this in 2 dimensions is more subtle in a rigorous manner, but there is, I think now there's a proof by Hastings, which proves that there is no trivial ground state for half-integer spins or even bosons at integer filling, in half-integer filling. We don't even need the local constraint. Yeah. So this is a simple example, the simplest case where you can see this, out of very simple algebra. But yeah, in general, the proofs are more complicated. Yeah.
I didn't understand why the algebra ruled out the trivial state. I mean, couldn't the x and ty just annihilate the state?
Annihilate the state.
But normally a state that is translation invariant, apply the translation.
No, this is e to the translator.
Oh, yeah, sorry. Yes.
Okay, it's not the momentum,
Okay,
yeah.
yeah.
E to the momentum.
Thank you.
Okay, I think it's square, I mean, it has to square.
Yes.
Nth power has to be 1.
It should be 1. Yeah.
So it can't just, eigenvalues have to be the roots of unity.
Yeah, sorry.
Is there a continuum field theory description?
Well, yes, and yes, there are certain anomalies. So there's some internal symmetry groups then. Translation becomes an internal group, and there is some kind of anomaly where you gauge the internal symmetry along with the, in some way.
The reference?
Well, for the Z2 case, it involves all these complicated cup products. I think there's a paper by Max Metlitsky and Ryan Korngren, I believe, has some discussion of it. But there's many versions of this same simple fact in many different contexts. The simplest, the original Lieb-Schultz-Mattis argument in 1 dimension is essentially a version of this argument. Okay. Right. I mean, if you can also define it on a lattice as an anomaly, but then you have to carefully define what you mean by. So
If you consider Tx squared, this issue doesn't arise. So it's only an issue of the Z2 of the translation. It's not full translation.
Yeah, there's another way to say this, which comes back to this picture. So as I argued, the addition of Vx is actually the same as inserting a flux. So now if you imagine you have a global symmetry, like bosons at half filling or something, then what you do is you gauge that global symmetry and you insert a flux on the torus. And you look at the momentum eigenstates of the states on the torus. So that's essentially the Oshikawa-Hastings argument, and Lieb-Schultz-Mattis is also like that. And you can write that as some sort of anomaly. Okay, so let's figure out what happens at large G. Okay, so this is something I mentioned briefly last time, but let me say a few more things about it. So the interesting case, of course, is eta equals -1. So G goes to infinity, eta equals -1. Then we had to have G sub I is -1 on every side. And the way you can arrange that is to have sigma x equals -1 on the least number of sites. Because every time sigma x is -1 at large G, there's a huge energy cost. So you want to minimize the number of sigma x's. So if you put sigma x equals -1 on this side, then what I do is I draw a dimer, and now I'll make it green to distinguish from that, which is sitting here. Okay. So there's sigma x is -1 there, here, in a way that every site has an odd number of G's, of greens. But you should only have 1, because if you add 3 of them, then it costs you energy 2G, which you don't need to pay. So this is a dimer covering of the lattice. This is the correct dimer mapping. And every such state is an eigenstate as G goes to infinity. So what happens at small, at very large but not infinite G is a very complicated question that involves doing some kind of effective theory of fluctuations of these among these dimer configurations. You have to write on an effective Hamiltonian on this space, which is called the quantum dimer model. And what we know is that for both the triangular and the square lattices, the leading terms as G goes to infinity are such that, in fact, the ground state breaks the symmetry. It's not a liquid, as it was a small g, but a non-trivial state, which will realize this algebra. And, so that a state like this would be something like this. So the dimers crystallize into some pattern, for example, this one. And now you can see, whether you have an odd or even number of sites is a totally different ballgame. If you have an even number of sites, you could fit these columns, no problem. If you have an odd number of sites, there has to be some defect line. And so things do depend on the geometry of the system. But in this case, the dependence is due to the broken symmetry, broken translation of symmetry. This is the valence form solid. It breaks all kinds of symmetries, but in particular, translations. And so this is our non-trivial ground state. It doesn't have fractionalization. It's not a state with half-charged particles like the small g state. But nevertheless, it knows something about the geometry of the system. And so, so it also has a lot of interesting properties, but they're not fundamentally different from the kind of properties we talked about in the first part of the course. Okay. Any questions? All right, so what I promised to do was say something about the nature of the phase transition. So now we believe for both G even and odd, we have some understanding of the grounds. What eta both plus minus
I'm
1.
sorry, quick question.
Yeah.
If I wanted to realize this algebra now with this cartoon state with a defect line, I'm a bit confused. What would I do? I would need to put the defect line at some momentum
Yes, yeah, correct. There'll be a 0 momentum phi state and a momentum 0 state. And the even and odd combination, and in the limit as infinity, they may have they'll have the same energy, something like that. Not sure. Maybe you can figure that out and let us know next time. I don't think I've ever worked it out. But I'm going to show you a continuum formalism, which hopefully will make that clear. Okay, so the question I want to address now is the nature of the phase transition. So as a function of G, now we have a phase diagram. Okay, so as a function of G, so small g, we have the Z2 spin liquid topological state. And then there's some phase transition at some GC. And on this side, we have a trivial state for eta equals 1 and a VBS state for eta equals -1. And this is the phase transition that we want to understand. So the first phase transition from here to here was in fact understood by Wegener. And the way he understood it is by a duality transformation from the pure Z2 gauge theory in the cubic lattice to the pure Ising model on the dual cubic lattice. So this is an exact transformation in exactly the same spirit as the Kramers-Wannier duality. That goes back to 1930s or something. You do exactly what Kramers and Wannier did, but do it on cubic lattice. And you can then take this Z2 gauge theory and map it to the Ising model. You can even do it exactly for the Hamiltonian version. Okay. And the Ising model, this is the 3D Ising model, 3D classical Ising model. That's what Wilson and Fisher understood. So that's the 3D Ising critical point. It's an interesting conformal field theory, and that describes the way the spin liquid disappears into the trivial state. So let me just actually get the same answer, but using tricks that will be more useful for us for this other case. So the way we want to do that is to first, we understood the ground state here at G equals 0. So I want to understand the excited states at G equals 0. And let's just consider the case eta equals 1 to begin with. So eta equals 1. What are the excited states? So this will be actually a homework problem where you can work out all the perturbation theory in detail, already in the problem set. So it's just a matter of doing the perturbation theory that we did for the ground state for the excited state. Okay. So now I should write up the Hamiltonian here. It's minus k, product of sigma z minus g sum on sigma x. Okay, so again, there's all this subtlety with making everything gauge invariant, but you can just pull that factor out and do everything on a given sector. It's easy to see what's going on, at least for eta equals 1 case. A little more subtle for eta equals minus 1. So the ground state is all spins up in some representation. Okay, so there's no loops anywhere. That's one of the allowed states in the expansion. And that was at k equals infinity or g equals 0. So now I come in and flip one of the spins with this to get an excited state. I'm going to make one of them down. And that's going to cost me energy 2g. No, sorry, 2k. Why is that? Because I have two plaquettes now. I have this plaquette here, and this plaquette here that have flux minus 1. Okay. All right, so that's what one action of G gives me. It gives me this state. In fact, this is an eigenstate of this part of the Hamiltonian. So now I will do perturbation theory on this state due to the effect of this. So the other thing you can now see, as you'll see right away, that there's actually an infinite number of states which have exactly the energy 2k. So we really have to do degenerate perturbation theory. But fortunately, it's not too bad. So for example, if I now take the same sigma x and hit it over here, then this has flux. This is repaired, and this has the bad flux. And this is another state that has energy 2k. And really, that's all I can do. Sorry, it's energy 4k, because there were two of them, each cost 2k. Sorry, so this is a bunch of states with energy 4k. And now I can see I can just move this anywhere I want and take the one out to infinity. So imagine I've done that. So there's a string of downspins here. And then I'm only looking at this object on its isolation. So this is the phenomenon of deconfinement. I created two particles, but there's so many of them, so many states that I can send the other one down to infinity. So there's a string here going out to infinity, and I don't worry about the other end of the string. So now I have to worry about the motion of this object on its own. So life is much simpler. It's just one object, not two of them, and it has energy 2k. Okay. And so what can this object do?
So is it 2k and not k?
This is the relative to the ground state. So the energy was minus k in the ground state, and now it's plus k. So the difference is.
Oh yeah, of course, yes, sorry.
Okay, so now this can hop. It can hop from here to there with matrix M and minus g. I can hop here, and hop there. So that's exactly a tight binding model of a particle, a single particle. And so this will give me energy 2g cosine kx cosine ky. After I go into the plane wave basis, you can work that out in your homework. So you get a particle with which disperses, has a certain momentum k. It can't be created on its own. This is, of course, the y zone or the m particle. This is the m particle. And it has some dispersion in momentum space with a minimum here. So this minimum is E 2k minus 4g. So that's the particle over here. We have a particle sitting there and it can move around. Okay. So when will something go bad? So now you can go to higher order perturbation theory. You'll still find that particle is totally stable. You might get some, 3-particle continua off there that you have to worry about. But this particle, at least in perturbation theory in G, will be just all on its own. Perfectly well-defined particle that moves to the left, has some mass. So this phase transition here, therefore, is something that very naturally is going to happen when this thing hits 0. And it's going to hit 0 at momentum k equals 0, which is okay. All right. The other thing you can see that this object is its own antiparticle. If you go to have more than one of them, they can hit each other and collide and get nothing, at least in terms of you can hit one operator in the Hamiltonian and create 2 of them. So that means they can also go back if the energy was present. Anyway, so there's a systematic way of looking at phase transitions what happens when this thing goes to 0. You can also view it as some kind of symmetry argument. But I don't want to go into it because that's a whole different subject of theories of quantum phase transition. Let me just give you sketch the answer. So when this gap becomes very small, I can take the continuum limit and I'm going to get here in the continuum theory a real particle of phi. So you can write on a path integral to phi.
Hello.
Yes.
Yeah, so is it important to send the other particle at infinity to get this kind of spectrum? I mean,
Yes.
What if hello?
Yeah, I'll come back. That's an important point, and I'll come back to it. But you're absolutely right. You do have to send it out. This is one particle on its own, but somewhere in the system, there should be another particle. So the particle is not observable. There's no experiment I can do to measure the phi correlation function, for example, 2-point function. Yeah.
So this is in perturbation theory where G is small, but the transition is where you balance the 2 cases.
Correct. Yeah.
So G is not small.
Yes.
Should you worry? I understand that qualitatively the picture could be trustable, but
Yeah.
quantitatively, is this trustable, or can we just solve the equation of when it hits?
No, absolutely not. So it would not give you such a good estimate of exactly where the transition is, the value of GC. I have no idea. We are going to assume that this picture holds smoothly all the way to the phase transition. And to really check it, you have to do, people have done series expansions to 20 orders in the Ising model and check that this gives you the right answer. Right? You do per day analysis and all of that. But right now we're doing the usual field theory guesswork, and assuming nothing happens, we can write down and propose what the field theory is that will determine the critical exponents, but not the value of GC. So what's the field theory? Well, I already gave you the answer. So you have a particle phi, a particle M that's created by a field. It's a real field phi. And you just write down the continuum Lagrangian for the most general theory consistent with these symmetries, and it turns out to have Lorentz invariance. Need not, but it does. So it's d mu phi squared plus some, let me say G minus, it's, so GC is where it's condensed, so it's GC minus G, some tuning parameter phi squared, plus U phi to the 4th. So this is the arguments for this are very similar to the arguments that Wilson Fisher went through for the Ising model, showing that they're described at low energies by the 5-fold field theory. And then this has, of course, been used by many methods, including Bootstrap, to figure out all kinds of properties. So this is, the Ising critical point. It's Ising, but one thing you have to keep in mind, and then there may be nicer ways of seeing it, I think Nadi can clarify that. In the condensed matter literature, we say it's Ising star. What does that star mean? The star means that exactly what the question asked, phi itself is a theory of a particle, but its particle doesn't exist on its own. Any observable, any local operator that you can make is only sensitive to phi squared. There is no gauge invariant operator that can measure phi. So what this means practically, what the star means, is that if you compute the critical exponents in an infinite system, there's no difference to the critical exponents of the usual Ising theory. But if you put the system on a torus, then you have to sum over different boundary conditions. And there are additional states in the conformal field theory. Some states are removed and some states are added. And there's some kind of like a global Z2 degree of freedom that you have to worry about. Maybe you can say that better than I can. How would you say it?
Synovial.
Okay, thank you. Synovial.
Phi goes to minus 5 here.
Yes, yes. Okay, for the young students, don't worry about those comments. I think for your purposes, really all you need to know is that Wegener showed this is the same as the Ising model. All right, so now let's go back to this calculation for eta equals -1. That's the fun part. Okay, so what's going to happen there? So now you do have to worry about all the gauge invariant factors, but the basic picture you can again see by just focusing on a representative in the big expansion of all loops. So here's our ground state, and let's say I have a Y-zone here. So that means there's a transcript going out to infinity, and I won't even draw the spins. So this means the spins are up on these plaquettes and -1 on this line, plus all kinds of closed loops on front of it. All right. So now what about this -1? Where does that come in? Well, the way it comes in is now I take this object and I move it here. That's giving me a factor of sigma x. And then I move it here. Gives me another factor of sigma x. So that's one way to go from here to there. But if I go the other way, go this way, here and there, then I get another sigma x here and another sigma x here, because sigma x is the object that moves the bison. So what I'm doing here is eta equals -1 and the small g excited states. All right, so now what's the difference between this way of going and that way of going? Well, that's the operator on the tx ty goes to ty tx. One is you act on whatever the state is, you hit first y and then x, or x and y. Those are the two different ways of doing it. And they differ by the action of sigma x, sigma x, sigma x, sigma x, which is gi on this side. So that's -1. So whatever this particle is, translations might anti-commute on its states. This is again an exact statement for any excited state of this spin liquid at small g. It's true to all orders in G anyway. And there could be a phase transition when this particle condenses, then things that will be up to true all the way up to DC, effectively. Yes.
Can we phrase it by saying that eta equals -1 is background electric field under the Z2, electric charge under the Z2?
Yes.
Since this particle carries magnetic charge, it picks a factor -1 as it goes around.
Perfect. Yes, you could say that. Yes, you could also say. So everybody heard that. So this is a magnetic charge. This flux, Z2 flux, is a magnetic charge of this gauge theory. And since there's electric charges on every side, because GI is dependent on the electric charge on every side. So when you take a magnetic charge around an electric charge, you think of a factor of -1. Or the other way around. We usually think of it as an Aharonov Bohm flux. When you take the electric charge around a magnetic charge, here you're doing the opposite. Okay, so this is the key point. So now we have to do play the same tricks we played for the eta equals 1 case, write down some field theory for this particle, which realizes a representation of this algebra, and take its low energy limit and find the critical properties. So that's a rather complicated task, which is worked out in full detail in the notes. I don't want to get bogged down in a lot of messy algebra, but let me at least sketch the path. So first of all, again, because the translations are anti-commute, this means that it can't be a non-degenerate particle. There's got to be at least two degenerate particle states to realize this algebra, even in the continuum limit. So the Wison cannot be non-degenerate. It's at least doubly degenerate. Okay, so that's in fact something. Now we're saying that the Z2 spin liquid, they're not exactly the same. In terms of some bulk topological properties, they're exactly the same for eta equals 1 and eta equals -1. For eta equals -1, this is a slightly different field theory in the quantum numbers that are carried by its quasi particles, especially particular translation quantum numbers. Okay, so you hear the flux moving around a charge, but let's think about it in exactly the way Mari said. Let's think of this as some electrical charge. So we'll just interchange electric and magnetic. So we just have a particle moving in a flux. So let's write down a lattice model of particle moving in a flux, pi per square on the dual square lattice. So that's what you have to do. Now we'll figure out the first order perturbation correction of the spectrum. So we're going to have eta equals -1. The particle moving in flux pi per plaquette. Okay, this is the kind of thing we're very used to doing for electric charges, but not for magnetic charges. It's essentially the Hofstadter problem. So the only thing is the dual lattice, that's all. So now the particles in the dual lattice, so let me just remember that. I draw the dual lattice with orange. It's hopping on this lattice. The white lines are the way the original square lattice we started with, where the spins are of the antiferromagnet. So we have a particle sitting here, and it's hopping around, and I want flux pi per plaquette, so I have to pick a gauge. And the gauge I want to pick, for example, one gauge would be, all these lines would be -1. Hopping would have the opposite sign. Okay, so now if I take the flux around any plaquette or any orange loop, I get -1. So this is, the discrete analog of Landau's gauge for this very simple Hofstadter problem with flux 1/2. Hofstadter does it for general flux P over Q. In this case, you don't break time reversal. And it seems like you've broken transformational symmetry, but you haven't. That's simply a gate choice. All right, so from this, you diagonalize this. You get a spectrum. So this is a homework problem to work this out in some detail. So you're going to get some spectrum. What happens there? Yeah, so I can give you the answer. In this, yeah, the energy is of course gauge invariant, so it doesn't matter how I choose it to get the k of these m particles, the root of some. Well, okay, I don't have it. It's 2k, 4k squared. Plus or minus. So I think you're going to get the answer in perturbation theory in your homework, something like this. R squared kx plus squared ky. No, there's no square root. So. Okay, something like that. I may have the factors wrong. Depends on the gauge, exactly how it works out. But just to sketch it, somewhere in the Brillouin zone. So this is some direction. Let's see which one did I pick. So, so I picked ky. So this, I call this direction ky. This is ky equals 0. This is ky equals pi. And there's some dispersion here, which has a minimum at ky equals 0. And then it has another minimum at ky equals pi, which is exactly degenerate. So for every particle state at this point, there's another particle state near pi. And yeah, and these are distinct points because the unit cell in the y direction has not been doubled. It's only been doubled in the x direction. So kx equals 0 and kx equals pi are the same point, but ky equals 0 and ky equals pi are not the same point. Okay, and these have exactly the same energies. And so what you have to do then is take a particle here, we call phi1, take a particle here, called phi2, and write down a field theory for the two particles. Okay, now you can take a continuum limit when this gap closes. And again, this algebra guarantees that the point where this gap closes is also the point where this gap closes. In general, this is a very general thing. If you have flux P over Q, there are at least Q minima that go to 0 at exactly the same point. And that, again, you can show by this type of algebra. All right, so now you get a field theory of not one real scalar field, but of two of them. And this is great because you need some gauge invariant degrees of freedom to be able to describe the broken symmetry here. So what will happen is that when these two fields condense, then something physical that you can measure will break the symmetry. When the single field condensed, because phi was not observable, there was no symmetry broken between here and here. You couldn't observe anything about phi. But here, there's the relative combination, the products of phi1 and phi2 are gauge invariant. And those transform non-trivially under translations and rotations and so on. All right, so there's a lot of fun algebra that you can now figure out the field theory. The field theory turns out to have like a D8 symmetry or something like that. That's all in the notes. I don't think I want to tell you much more. Yeah.
Sorry, again, I'm trying to understand.
Yeah.
These funny algebras with Tx and Ty.
Yeah.
T square is never funny. T square is not funny.
For this case, yeah, with h I equals minus.
Square is what obviously becomes momentum. The translation in the continuum. So Tx is an ordinary internal symmetry.
Right.
So this is the one that just swaps.
Right. So if you look at the full symmetry, including lattice rotation, there's also a symmetry of rotations of x and y. So the full group turns out to be a non-abelian group, which is D8. So, okay, let me just tell you how it works. So all the algebras in the notes, it's a matter of taking the field over here, the field over here, understanding how they transform under translations, both in the X and Y direction, and understanding how they transform under 90-degree rotations. Those ones are more complicated. They're like a Hadamard operator. They will involve a rotation in the 5-1-5-2 space. And all of those operations are such that the square root of t is 1, and the fourth power of rotation is 1. But you can have complicated things like happen like this one. So anyway, so there's some, in fact, a non-abelian group. Or it has to be because dx and dy have complicated algebra, and it's the group D8. So the full set of symmetry operations that that generate the symmetry of the field theory. So you get here's the way I've written in the notes. There's a field theory for a complex field. This is a Z2 gate charge, but it's at this phi is okay. There's many ways of defining it, but this turns out to be the most convenient one: e to the minus pi over 8 phi 1 plus I phi 2. And then you can take this operators that act on the Hamiltonian, which commute with it, particular translations and rotations. And the operations turn out to be Tx takes y to e to the I pi 4 y star and ty minus I pi over 4. This is on the square lattice. Life is even more complicated on the triangular Kagome lattice. And you get even more exotic groups there, which we have worked out. R pi over 2. Okay, so all of these have been cleverly chosen so that at least rotations by 90 degrees are simple. Pi goes to pi star. Okay, so these are the operations of the physical symmetries of the Hamiltonian on these fields. And now you can take products of these operations in any way you want, and you'll find that that generates a group, and that group turns out to be D8. So the full symmetry of the continuum theory in this phi language is the group D8. So that's the diusual group of 8 elements. You can look it up in a group theory book. But you don't really need to know that to write down the field theory. So what is the field theory in the end? So now we're going to, we are addressing what's the field theory for this. All right. Spending too much time on this, but I spend a lot of fun years working on these kind of things. So what's the field theory? So you want to write on the simplest Lagrangian consistent with these symmetries. And that turns out to be the XY model plus some R mod phi squared U mod phi to the 4th. But not quite. There's another term. The simplest term is twice lambda. And it's phi to the 8. It's phi star to the 8. Okay.
1 of the 4th should be a square problem.
Oh, thank you. All right, so if you know a little bit of field theory, then you can see that these are what are called irrelevant perturbations. They don't change the nature of the critical point. And the first 3 terms describe the XY model. So this is the finite temperature transition from the superfluid to the normal state in liquid helium, for example. And so this transition is XY, but it's also a star because phi itself is not observable, but phi raised to some power is observable. And in fact, there's the VBS autoparameter, which basically turns out to be phi squared. So now phi squared is not trivial. Phi squared is something interesting. It can be measured because it's gauge invariant. So there's a broken symmetry, and that's the VBS autoparameter. Now, if you ignore these terms, it's as if there's a continuous broken symmetry, but those terms reduce it down to a discrete broken symmetry. So they are what's called dangerously irrelevant terms. Right near the critical point, it seems you have a continuous broken symmetry, but the moment you move away, you realize it's discrete.
Subir, I have a
Yeah.
question. So D8 as a group has a center. How does that center act on this operator? Does it always act as -1?
What is the center? Sorry.
There's a Z2 center of the D8 that commutes with every.
Well, that's the gauge symmetry. Yeah, phi goes to -5. Yeah, that's the part that's not observable.
So it always acts as -1 on these operators.
I believe so. Yes.
Thank you.
Now, there's other ways of interpreting this using U1 gauge theory is broken down to Z2 and so on. And U1 gauge theory is a monopoles. And so these turn out to be like the fourth power of the monopole operator and so on. So there's a long story there, which really would be out of place for me to discuss here. So these are, in that interpretation, typical of the instanton type terms we get in many gauge theories. Okay. All right, I think I've spent too much time on that, but it's, as you can see, very beautiful, at least I think so. And it all comes from the very simple fact that Tx and Ty don't commute, which, as I showed you very simply, is related to the fact that there's background electric charge.
Excuse me, what did you mean when you said the phi terms don't change the nature of the phase transition?
Well, because they're irrelevant at the critical point. So all the critical exponents of this phase transition would be the same as at lambda equals 0. It's just that if you compute certain correlation functions, you will get corrections with decay faster than the leading term due to the lambda term. So there'll be some additional corrections, but they're sub-leading. That's at the critical point. The moment you move away from the critical point, then it has a much stronger effect. Because if you move away from the critical point when phi condenses, there's a Goldstone mode, which has 0 energy, but it doesn't have 0 energy here. So the Goldstone mode with the spin wave mode gets a small gap, and that gap is proportional to lambda.
So is the statement that GC is not dependent upon lambda?
No, the critical exponents in GC are not dependent. There's another fun way that we'd like to draw this. So if I draw an RG flow, so this is G. Well, G is like R here, sorry. GC minus G. Right, so there's a critical point here at GC. Let's make this the lambda axis. So at this point GC, lambda goes to 0. So if you're really interested in the critical properties, lambda is 0. And the flow here is this way. So this goes to G equals 0. Strong G is the phase you're interested in. So what happens here is that if you're a little bit away, lambda seems unimportant, but eventually it comes out here, and at this point is very important. So this is what's called a dangerously irrelevant variable. So it's irrelevant, but there's danger because you're just slightly away, it's going to come back and give you the gap. Back gap out your Goldstone mode, because G equals infinity is in this language the point where you have a Goldstone mode. And at that, for the Goldstone free field fixed point, this term is very important. It flows to infinity. Okay. And this is a good RG flow to keep in mind. It shows up in many, many places.
So is this Lagrangian is dual to any other field like XY model and like in particle vortex duality? The XY
This
model
one?
is dual to the this one.
Yeah, so you may know, for example, that the XY model is dual.
This is dual to Abelian Higgs model.
Sorry, I can't hear you. Say that again.
Yeah, I mean, is there any dual theory of this Lagrangian?
Yes, I'm telling you. So if I remove this point, then this is the Abelian Higgs model. So that's a well-known duality where you take XY field theory and it's dual to a scalar coupled to a U1 gauge field with no monopoles. And this term then turns out to be a source term for the monopoles, but higher charged monopoles. And there's a factor of 2 somewhere that's very subtle, but okay, we'll do it. The monopoles in phi are actually the naive monopoles you would think when you take the duality have flux 4 pi, not 2 pi. So in fact, this is actually charge 4 monopoles. But anyway.
That's because of the Z2 gauge theory identifies pi with minus pi.
Okay, I think that's correct. All right, so I have 25 minutes, so let me get to some very current experiments. All right, we're going to find very close to this Z2 gauge theory actually being studied in experiments, really for the first time. So these are experiments in my colleague Misha Lukin's group at Harvard. There's also another group at Paris, which is doing similar studies. So what do they do? So first of all, they have these tweezers. And don't ask me too many details. So there's a bunch of tweezers that they can very cleverly arrange in any arrangement in any lattice you want, 2 dimensions. And they put an atom, just one atom, in each tweezer. So this is my atom. Okay. So the atom has a ground state. This is the state G. And then it has some excited state that's quite long-lived, and it's a very big state. So there's a state G, and let me say there's a very big state. You can make the atom really, really big in the state R by sending in a laser. So there's all kinds of lasers here. There's the lasers which are forming the tweezers. We forget about them. But there's a couple of other lasers coming this way. And I should really draw this the other way around. This is the Rydberg level. And then there's a ground level here, which is a very small atom. Okay, so you have these lasers which can take this atom from the ground level, but it's a very small atom, to a very big atom. 10,000 bigger. It's amazing how big it is. I think Rydberg number is around 80 or something. And the radius of this orbital, this rubidium atom, goes to the 4th power or something, okay, of the principal quantum number. So it's really huge. Okay, so now what happens is that you have something called a Rydberg blockade. So this is a 2-level system which you can bring on resonance with a laser. Fine, if you just have one atom, you can study that. That's been studied, for years. What happens is that these atoms are close enough to each other. If the 2 of them want to be in the same Rydberg state, there's a problem. So this thing becomes big, and this becomes big. Well, that costs a lot of energy. So this is not going to be allowed. So there's what you call a blockade, which prevents nearest neighbors from becoming big. So you're exciting, these atoms are oscillating back and forth between these 2 states. But they're not independent. So if this one happens to be up, the other one has to be down. Right? At least the near neighbor sites. So that's it. So that's the system, and I can write on a very simple Hamiltonian for it. What I'm going to say is that this ground state, I'm going to identify as the empty state. And the excited state, I'm going to say there's a hardcore boson in it. Every time atom is excited to Rydberg state, I say there's a boson there. Okay, so what is my Hamiltonian? Now I can write down the full Hamiltonian and then forget about the atomic physics. And we're just going to study that Hamiltonian. So this Hamiltonian was actually proposed by Paul Finley, Sengupta, and myself a long time ago in a different context. So this is the FSX Hamiltonian. So I'm going to put the atoms on site L. That's, you might anticipate, because I want L to somehow be a gauge field. But right now, that's just for obscure reasons. So I have what's called omega over 2 BL dagger. What is omega? Well, omega is called the Rabi frequency. So that's the proportion of the intensity of this laser. That the intensity of the laser controls omega. How rapidly you're going back and forth between two levels. Okay. Then there's a term which is delta B dagger L BL. So delta is what they call the detuning. So this is a very clever method where you can forget about the laser actually also. So you imagine the laser comes in, these two levels are really far apart, but in the presence of a laser, this thing gets shifted up to some state here. So this is the laser frequency, omega L. And so delta, well, delta is, well, let's say it's blue shifted. So this is omega L, it's slightly above. So the ground state gets shifted up to here. This is the Rydberg state. This is the shifted ground state. And this thing, this distance is delta. It can be very small and in fact comparable to the Rabi frequency. And in fact, the whole game is tuning these two. And if the lasers assume to be completely coherent, we forget about any decoherence in the laser. We forget about spontaneous emission, the Rydberg state decaying to other states, and so on. So these are important details that, of course, took many years to get right, but as theorists, we don't worry about it right now. Okay, so this is the Hamiltonian for a single atom in the what's called the dressed atom basis, or the rotating reference frame of the laser. And then there's the interactions, which are the repulsion between the Rydberg states. So there'll be some on L, L prime, on path, some potential V of RL, L prime, B dagger L, BL, B dagger L prime, BL prime. And then, of course, we have to remember the constraint, B dagger L, BL, can be only 0 or 1. Okay, so that's the whole story. And now we can forget about the atomic physics. This is the Hamiltonian we want to understand.
This is a two-dimensional, right?
So the experiments were initially done 1D. There were a lot of experiments in 1D, which is also a very nice story. The 2D work is as of this year. Yes. So now they have up to, I don't know, 300, 400 atoms in a 2D array. Coherent over appreciable time, so you can measure the coherence between different atoms. Okay. So this is a quantum simulator. Maybe someday it'll be a quantum computer. But right now, what I'm going to just argue that it's actually Z2 gauge theory on the right sort of lattice. Okay. So everyone with me, any questions on the, well, I probably won't answer them in detail, but this is roughly my picture of the atomic physics.
Excuse me, sir.
Yeah.
So can you translate this Hamiltonian to the Pxp model?
I'm coming to exactly that, yes. The Pxp model is a version where V is either infinity or 0, then it's for certain sites, and that's the Pxp model. Well, the Pxp model precisely is delta equals 0 and v equals either infinity or 0. But some versions of Pxp model have a non-zero delta. Yeah, in any case, all of those versions were discussed by us a while back. Okay. So the first thing I'm going to do, so for a while, I'm not going to make any approximations. In fact, for quite a while. And I'll show you that this can be rewritten on suitable two-dimensional lattice as a Z2 gauge theory. Now, at some level, that's an empty statement. You can always take any model and put in enough fake degrees of freedom to make it a gauge theory. And however, for it to be useful representation, when people say they've got a gauge theory in their system, what the first question you can ask is there a deconfined phase? Are you close to a deconfined phase? With the gauge degrees of freedom, the gauge charges are nearly free. If you don't have such a condition, then it's not a gauge theory. You can say quarks are never free, but there is a condition at very high energies where they're nearly free. And that's why we think of the strong force as a gauge force, not for any other reason. Okay. So that's the similar question we're going to ask here. So the first thing I'm going to do is I'm going to map these two spins. And so I'm going to take BL, this BL dagger, and map that to sigma Z. This is the confusing part always, what I got confused last time. So the raising and lowering operator is the sigma Z operator. And the number operator is the sigma X operator. So this has eigenvalues 1, and so sigma X plus 1 over 2. So this is eigenvalue 0 and 1. And so when sigma X is plus 1, I have eigenvalue 1. And when it's minus 1, I have eigenvalue 0. Minus 1. 0. Yeah, this is 0. Sorry. Okay. Yeah. All right. So with this substitution, I'm now with complete accuracy, no approximation, since the number of bosons is 0 or 1. And now the Hamiltonian is a model of spins. Okay. Again, so far, I have omega sigma Z minus delta sigma X. And then I have this term, prime V of prime 1 plus sigma X L over 2 L prime over 2. Okay. All right, this is just fun and games, writing things in a form that I like. All right, so but we've been seeing gauge theory, so it's of course very suggestive, and a gauge theory the sigma X term, but it had product of sigma Z around a loop. This doesn't quite look like that. So our hope is that these interactions are such that effectively this model looks like product of sigma Z around a loop. Okay, so all right. So let me give you the rough argument of when it doesn't always happen, but at least in a certain theoretical model, there's now good evidence of that happening. So let's see. Now I have to actually draw the lattice. Okay. So I have to draw a Kagome lattice. And so this, okay, I should say that the connection to Z2 gauge theory was first came up in work done by my student, Ryan Samazar. And that connection is slightly different than the one that I'm going to describe. This one works better, and this was proposed by Ruben Verison and Ashwin Vishwanath. But most of what I'm going to say holds to both cases. Okay, so let me see if I can draw a Kagome lattice. And probably too many.
This is the lattice because for some reason it's easier to make for the atomic physicists.
No, they tried other lattices and then you don't get a deconfined phase.
Oh.
This is the lattice for which these V, so you don't have those sort of, what stops us from being a quantum computer is that we can't really control this independently. Well, you can put the atoms somewhere and wherever they are will determine these numbers. And the positions that you're going to choose, as I'll show you in a minute, are ideal in this lattice. And maybe others, but this is where the proof is fairly simple. So, okay, so this is the Kagome lattice, and you're going to put the atoms on the links of the Kagome lattice. You're going to put them here. This is where the atoms are. These are the Rydberg atoms. Okay. So the L sites, this is where the atoms are. Okay. All right, so now someone asked about the Pxp model. So the simplest way to see this is to make the Pxp model. And so what we're going to imagine, at least for now, that we are able to tune these couplings as we want them. And we're going to tune them so that the first, second, and third neighbors are prohibited. So if I put a Rydberg atom here, it's big enough so that this interaction, which I call V1, that's the first neighbor. This is the second neighbor. This is V2. Sorry. No, this is the first, excuse me. That's the second neighbor. This is the first neighbor. This is V1, and that's V3. So we're going to take V1 equals V2 equals V3 equals infinity, and all other V will be 0. So let's just start from that limit when things become evident why this is a gauge theory. Okay, so what that means is that if I, let me draw the big atom in the green. So I put an atom here, and that's excited. So the moment that this atom is excited, all these atoms here can't be excited. In fact, I've cleverly chosen this so that if I think of this atom as a dimer, there's a dimer here, they can't be, the dimers cannot touch. Okay. All right. So that's, and so to optimize this term, I put in dimers everywhere, provided they don't touch. And then my energy for this term would be 0. Okay. So then what should I do? Well, so this term is always acting. It's creating particles out of the vacuum, flipping particles, creating Rydberg states. Sigma z is B plus B dagger. And this term, let's imagine delta is becoming large. And so we want to optimize the number of Rydberg states. So we are pumping atoms to the Rydberg state, and we want to pump as many as we can. So that's when delta is large. So you're tuning delta, and then you're putting more and more atoms in the Rydberg state. So what is the maximum number of Rydberg atoms for this model? Well, it's clearly the dimer packings of the Kagome. There are many different packings that are allowed, and so on. So maximum number of Rydberg atoms, max allowed number, equals dimer packings. So this is wonderful because remember, in the large G limit of the Ising-Gauge theory, we also have dimer packings for odd eta. So effectively, we're getting the same Hilbert space in this limit. All right, and now, of course, so this, any packing is an eigenstate of this term. It's also an eigenstate of this term, but it's not an eigenstate of this term. But as written, this term is not very friendly because it either add a dimer, if you're one of these optimal states, it's either going to add a dimer where it's not allowed or remove it, in which case it costs you energy delta, and you're assuming delta is large and positive. So it's going to take us out of the dimer subspace. So we now have to do degenerate perturbation theory. This is the hard part here. You have to do degenerate perturbation theory and look for, what are the allowed moves, and you get a whole bunch of allowed moves involving the usual RVP picture of resonating dimers. So now it's really a matter of taking this model and solving the effective dimer model. That's quite a complicated thing, but the simpler thing you can do directly here is just solve this model, which is the Pxp model for these particular exclusions. So this is what Verison and Vishwanath have done, and they have very convincing evidence of a 4-4 degeneracy on the torus and everything. You get all the properties that I've just talked about. In this Hamiltonian, if you just take this particular set of interactions. And there are also experiments which, the experiments of course are not in this limit, but they're close to it. And you can measure certain, the Vx and Wy operators in the experiment is very beautiful. And there seem to be at least some off-diagonal coherence and also the states with dimer packing selected. But I think it's too early to say that the Z2 spin liquid has been observed, but they're very close. Okay. Let me also say one more thing. So that's, exactly how things evolved in the past year. But let me actually look at this and try to say this in a slightly more general way. So what we have done here is, we have a term here in the original Hamiltonian where you can add and remove dimers. And that's not the kind of term we had in our Z2 Gates theory. However, we can make this a Z2 Gates theory by introducing a matter field. So let me introduce another set of sites, which are called the I sites, which are the vertices of the Kagame. So these are the I or J sites. And I'm going to change my Hamiltonian slightly. I'm going to replace this by someone Ij, nearest neighbors of tau Zi, sigma Zij, Zj, and then minus sub 1L, sigma X. Okay. So what is this theory? Now it's a Bonafide Z2 Gates theory, which is exactly equivalent to the original model. So this theory here and this theory there are exactly equivalent. But this theory has a gauge invariance and this doesn't. And it differs from the theories we met so far, well, at least the one we talked about today. It's not a pure gauge theory. It also has a matter field, tau Z. So tau Z is another set of Pauli matrices. I've introduced on every I site. So there's a tau Z I and there's a tau Xi. And now you can see that there's an operator that commutes with this Hamiltonian, defined on GI, the tau Xi, and product on L next to I of sigma Xi. Oops, there's a minus n there. So this generates a gauge transformation where sigma ij goes to sigma, what did I call it, rho I, Vij, j, and tau Vi goes to rho I, Vi, and sigma x goes to sigma x, and tau x goes to sigma. So here's an exact symmetry of this Hamiltonian, which is generated by this gauge charge. And now you can see that I can always choose my gauge, so I, to make tau z equal to 1. So if I choose the gauge where tau z equals 1, I'm back to this Hamiltonian. So I have an this tau is called an Ising macro field. So it's not a pure gauge theory. It also has matter fields. And initially, you might think this matter field is zero energy and will condense and destroy any Z2 gauge structure. And normally that's what it does. So you never bother to do all this. But when you have these kinetic constraints coming from these terms, you find that effectively, every time you create a tau x charge, that costs a lot of energy. And therefore, this is a good way to write the Hamiltonian. So in fact, the way to think about this, another way to think about what I told you earlier, is you have an Ising matter field, which has charged tau x. And every time that matter field is around, it costs some energy. So you integrate it out, and you get a pure gauge theory, which will be just described by exactly the kind of terms we had before. So now if I integrate out tau x, which is another way of talking about the calculation I described earlier. So we integrate out tau x charges. Then what you get is the effective Hamiltonian is exactly the gauge theory, but now on hexagons of sigma c minus g, in this case delta, times sigma x. So the key is really you can introduce matter fields, but you want to make them expensive. And the reason they're expensive in the end is because of this term. And it's kind of a subtle argument how that all works out. But anyway, so this is another route to obtaining a Z2 gauge theory in a way that you're close to a deconfined phase. Like I said earlier, if you're not close to a deconfined phase, that's an empty statement because you can always add plus or minus ones and make them gauge dependent, and so nothing will happen. But here, because these tau x charges are expensive, it is essentially a pure gauge theory. All right, I think I'll stop there. And that's it for Ising gauge theories. Any questions? Yeah.
So translation invariance was important in today's discussion.
Yes.
But of course, a real system has disorder.
Yeah.
So I assume since we're discussing it, means the results are robust despite disorder. The difference between 8 equals 1 and -1 was rigorously proved using exact translation invariance. But we hope it is true even for disordered systems.
Well, very little is known for disordered systems. I mean, I don't think we know if it's true. I mean, the translation operator doesn't commute to the Hamiltonian, and what will happen in a real system. I mean, an interesting question is, what is the nature of the confinement transition in a system where the gauge charges are equally plus or minus 1 in random configurations? That's, I'm surely a different universality class that's not understood. That's really an open problem.
That's a much more extreme case. I was imagining. I was merely trying to ask whether weak disorder.
Weak disorder is almost certainly also relevant. You could go to the field theory and put in some operators like that. Yeah, they're, yeah, I mean, what is already relevant is the position, fluctuation in the position of the critical point, if nothing else. But there can also be impurities which have a different gauge charge. So you just you're putting in Wilson lines at random positions in the field theory. That's also a relevant perturbation. Yeah, those all lead to very difficult questions of the type I was thinking about a lot until, I was led to the XIII model as a limit. Again, things could be solved with disorder. Yeah. Any other questions? Okay, so see you on Wednesday, and there won't be any classes next week. Wednesday, I'll go back to the other gapped spin liquid I began the discussion of spin liquids with, the Lofgren-Kolmar state or the Z2 spin liquid, and I'll say a little bit about it.